because not all of it is as important as other pieces. But again, if you realize you have a question, you know me, you can get up, you can move around a little bit, write a question up, or you can ask it verbally, either one. That's what I'm looking for. Where's your pass?
God, they're all down here.
I'm going to email them. Because so we're going to quickly go over some of the DYU, and then we're going to use some of the book work that I don't think y'all got into yesterday to tie it all together before I have to cover a couple of concepts, big ideas that I did not get to. Once again, I gave you solutions to the DYU the way I did it. There's other ways to justify some of these things. You can make notes if you need to. I did not. I got through 5 or 6 of everyone's front and back. The rest I got through the front. But right here, with number 1, I'm going to go ahead and go over this one pretty intensely because this is actually one of the book pages that we're going to look at later. So go ahead and write some notes as we do this so that you have that as a reference as we go through it later. But write the most precise factored form equation you can for the function shown. So what do we need if we're going to write the factored form? Did I hit record on that? This was blinking? Okay. What do you need? You got to have x-intercepts. Now, do you actually have to have x-intercepts? What do you need? Say it louder. You need roots, right? Because what could some of those roots be that would not be x-intercepts? They could be imaginary. Now, I will say, if you're given a graph like this, Caleb, you have to have x-intercepts. Because can you see imaginary roots? No. So we're going to use our graph to help us write this equation. Now, Damon, if I'm going to do factored form, what is that factored form? Not for this equation necessarily, but just in general, how do we write factored form? I mean, we do have some parentheses in there. What might go inside those parentheses?
X.
Uh-huh.
Minus.
Uh-huh.
0.
Minus what?
0.
Are all roots 0 though? I think they have a 0 involved, right? Can anyone remember? Let me ask this, Damon. Do you remember what the factored form of a quadratic was?
Yeah.
Okay, we need to know this. Okay, we've been working with this. John, what are you about to say?
It's a times x minus r1 times x minus r2.
So remember, that's the factored form of a quadratic. Remember, it's x minus our root. That's why we need our what, Caleb? We need roots, really, right? Now, Tori, do we only have 2 roots in this graph over here, in this function? You're saying no? How many do we have then? Say again. 4? Yeah. How do we see those 4, Caleb? You kept saying it earlier? Looking at the x-axis, at the x-intercepts. So, how many x minus r's do I need? Say louder. 4, for those who couldn't hear. And so you need to identify these roots. -2, -1, 2, 3. Now what do you have to be careful about that some of us made a mistake when we substituted our roots in? Pay attention to this and be careful about this. What do we have to do when we substitute those roots in? Yes, so we know that. Okay, so two things. One, make sure you have f of x equals. We don't know a yet, but what I'm saying is, for this root right here, what would I write? X? Is it x plus 2 or x minus 2? Why is it plus? You always need the opposite. Remember, we talked about that. Because if I subtract a negative, what is subtracting a negative the same as? Adding. Like that's what we get when we subtract a negative. We always end up with the opposite, right? So it had to be x plus 2, then x plus 1, whew, then x minus 2, and x minus 3. Now, I let it slide because I wasn't here to talk about this yesterday. Do notice it asks for the most precise equation possible, right? There's my roots. Because just based on our roots, how many equations are possible? Just based on the roots, how many equations are possible? Say a letter. Infinitely many, right? But I've got an actual graph here, not just roots. There's a specific equation for this one. Does anyone remember how we figure out what A is if we actually have some points like this?
Substitute. I think it was x for 0 or something.
Well, and so really it could be any point that we can clearly identify. So for example, this point right here is 0.5, comma 14. I could substitute 0.5 in for what? For x, and 14 in for y, or f of x, right? So I could do that, but I will say the y-intercept is typically the easiest. Notice, if I substitute 0 in, what do I get out? 12. So I'm going to substitute my input in, I'm going to substitute my output in, and so f of x becomes 12. Do I know what a is? Do I know what x is? 0. Do I know what x is? Do I know what x is? Yep, thank you, there we go. And x is?
0.
Okay. And so notice I now have an equation with only one unknown, that a. 2 times 1 times -2 times -3. Now, hopefully we know how to do this, but if we don't, what do we have available to tell us what this is? Calculator. So, anyways, -3 times -2. 6, right? Negative times a negative is positive, and 2 times 3 is 6. What's 6 times 1? Still 6. And what's 6 times 2? 12. Okay. Use a calculator if you need to. But what does A have to be to make this equation true? A has to be... Notice I could divide both sides of the equation by 12, right? 12 divided by 12 is 1, but also A is quite literally equal to 1. Okay? A is quite literally equal to 1. That's what makes that equation true. So, my final answer here is... That's the most precise answer I could write. Not just a generic A, but I could actually come up with a 1. And know that. And I think I don't show that work on... Did I show that work on my solution set? Yep, I did. Yep. Okay. Number 2 says... Oh, it says convert the equation from number 2. I'm going to say number 1. But convert the equation from number 1 into standard forms, because I moved one question around. How do I convert that into standard form? The area model. Remember, the area model helps me what? Starts with a D? Distribute. Remember, the whole idea is I needed to distribute this x, I need to distribute this 2, but it gets a little messy when you have 4 factors like this. So, area model to help me distribute. And there's several ways to do this. I think quite a few of us in this class, which is perfectly fine, took this, and so be careful. I saw a lot of just procedural mistakes. We took that x squared plus 3x plus 2, and then we multiplied that just by the x minus 2, which can 100% get you to the correct answer by the end. And once you do this multiplication, you have to do the last factor, okay? So hopefully this is a quick recap. Nope, that's minus 2x squared. Plus, minus. Man, I am struggling today. There we go. And then you just keep multiplying, okay? But personally, what did I, Mr. Kinney, do? Instead of doing it that way, where I then multiplied by x minus 2, then x minus 3, what did Mr. Kinney do? So I did this set of factors, right? And then I did this set of factors. And then I multiplied by the end. I'm not going through the whole thing because you have the solutions there, but notice I just did 2 at a time, and then I rewrote it as this became x squared plus 3x plus 2, and x squared minus 5x plus 6, And now when I use the area model, how many rows and columns do I have? Three by 3. Okay. Just again, be careful as you're multiplying it out. So that's my personal recommendation. Can you do it this way? 100%. Okay. This just becomes more efficient in my mind. Okay. Questions through number 2. And the reason I went through that a little bit more, and I'm going to reference it later, is because we use one in the book like that. Okay. How do you answer number 7 better? Number 7. So there don't really seem to be any questions about 3 through 6. What's the point of a relative extrema and why do we need it? I forgot to put it in there. Got the first slide, but not the rest. Okay, so a relative max, relative min. One of the big things is, one, I have to teach it to you as part of the course of study. And so if you're asking, why do you need relative max and relative min for life after high school? There's a whole bunch of concepts in business and in physics called optimization. And when we talk about optimization, we may want something to give us the most profit or maybe cost the least or something like that. And we track data and we look at functions for that regard. So it's not exactly the same, but if I was asking, hey, when would I have the lowest cost, where would that be on this graph? Which again, ignore this context. But if the context was, hey, where's the lowest cost? Where would the lowest cost on this graph be? Guys, it's not a rhetorical question. What have we studied that might connect to the lowest of something? What is that? Relative minimum, right? That optimization, we may be looking for the lowest of something in a certain range. A relative minimum. Or if I wanted the most, in this case cell phones sold, where might I be looking after that minimum there? Because obviously you're going to have the most sold right away. People are flocking to get the new cell phone. But after that initial couple of days, when do we have the most number of cell phones being sold? Huh? About day 25 at the relative maximum. So if you're asking the question of, hey, why do we need relative extrema? That's why, because it's all about what's called optimization, where we see maximum and we see minimum and these different things, because we want to optimize processes in life, etc. So it's really, really important in the world of business. It's really, really important in the world of engineering, but also we have to learn it for Algebra 2. Okay. Do I need to go over relative extrema? How to justify that? Good talk. Okay, if there's no questions, I'm going to continue on. You have examples there. Don't forget, it's a relative minimum because what's happening there? It stops decreasing and starts to increase. Thank you. Caleb, at least, has it. What about this one? Relative max y. So it stops increasing, starts decreasing. Remember, that's why extrema are really important for domain intervals of increase and decrease. You need your extrema for that. Domain and range, a couple of things I do want to point out here. We need to work on how we justify. I saw at least one student do a great thing that Mr. Kinney literally said, do the thing. Domain, when we see that word, what should we be thinking about? X values. Someone actually listened to Mr. Kinney and wrote that. Range. Y values. And when we do our intervals for the domain and range, what always comes first? Minimum. And so someone wrote minimum x and max x. And I will point out, I think I put 2 different sets of answers on my answer key, because if I'm just looking at that graph, when does it quit going to the left? It never does, right? So what's my minimum x? Negative infinity. By the way, don't forget, x values are also called what? Starts with an, no, I'm not going to tell you that yet. What's another word for an x value? Say it louder. Do not forget, x values are your inputs. Okay? And so what was the maximum x? When does it quit going to the right? Infinity. Range. I need the minimum y and the maximum y. So I've got negative infinity to infinity. I need to emphasize, a lot of people go from the top down, but is positive infinity the smallest value? No. It's got to be the minimum to the maximum. Pay attention to that. But contextually, I want to point out, we're talking about time of days since a cell phone was released, right? Can you go back negative infinity days? No, what's the first value in that cell phone release? Day 0-ish. Really, maybe you could make an argument for day 1. Mimi, do you need to stand up, move around a little bit so you're not falling asleep on us? Get that blood flowing some? No? Okay. So really, you could say 0 or 1 here, and what would be the maximum days according to this graph so far? It just has to be an estimate, but 28, 30, 32, well that'd be 32 right here, so maybe 33 or 34. So maybe day 33. Now granted, I think it literally says first 30 days. Range, right? What's the minimum amount of cell phones sold? I guess I'm going to look at it right there. How many in a day? That's 25. That's in between 0 and 50. You can make the argument 0. I think that's what I put on there. But looking at it again right now, I'm thinking 25. And what's the maximum number of cell phones sold? Depends on what day you defined as your independent or your day, your domain. If you started day 1, how many cell phones were sold? 254. If you did day 0, we'd be talking about 300. Okay? So context matters. Keep that in mind. Okay? Context matters. Okay, super into it, got it. This is the only place that people have really asked questions about. I will point out, I had at least one person, actually several people I believe, tell me that this is a 4th degree because there were 4 x-intercepts. Or sorry, 4 terms, 4 extrema. But we've got to remember, look at your end behavior. Could this be 4th degree?
No.
Why not? So the end behavior is different, right? It can't be 4th degree. It had to be an odd degree, okay? What was the possible, what degree could it be? Which degree? 5th, right? So n is probably equal to 5. Why? Because 5 minus 1 is equal to 4. Remember, n minus 1 is the maximum number of extrema. And so the fact that there's 4 extrema should have led us to 5th degree. Okay? For those of us asking about number 7, I need you to remember, imaginary zeros always come in what? Pairs. And that makes sense because we have how many real zeros? We have 3. 3 real zeros, each one with a multiplicity of 1. So the last 2 must be what? Must be imaginary. That's it. If there's 3 zeros and I'm saying it's 5th degree, there have to be 5 zeros, then that's what we got. Am I hearing things? I guess so. Okay. It's looking good. Well, you're coming back, aren't you? Because we got, okay, yeah. All right. So the last two must be imaginary. That's the justification. I think at least a couple of students said, oh, there have to be imaginary here. The idea, I think, is because there's a turn. But remember, quite literally, imaginary are imaginary because we cannot what? See them. You can't see those imaginaries. That tells us that there's imaginary, but that's not where the imaginary are. The imaginary would be nowhere on this graph. Okay? So, the fact that it's 5th degree tells me there have to be 2 imaginary. Making a note of, hey, imaginary zeros always come in pairs, something like that would have gotten you to that next level of evidence of understanding. Tracy, you with us? Makes sense? Jotty, you just crushed it so much you don't need any of this information?
Sure.
I know, it must be tough to have a teacher who wants you to learn. The villainy. Okay. So are there no questions about number 8? Or questions about 6 and 7 before I continue? All right, questions about number 8? None? Okay. Please note, what important concept tells you that there are 9 zeros in this function? That's not a concept. Yes, the highest power tells me there are 9, but what connects the highest power to the number of zeros? Fundamental theorem of algebra. Guys, you'll notice if you look at my solutions, and I wish I'd been able to give you feedback on everyone's back side of the DYU, you've got to recognize that there are 9 zeros because of the fundamental theorem of algebra. That fundamental theorem of algebra tells me whatever the degree is, that's how many zeros there are. We get on that? Okay. But we don't have to have that many x-intercepts. What do you say, Emily?
I stopped with the algebraic theorem. I didn't have the right one.
Yep. It's called the fundamental theorem of algebra. I'll let that count as some evidence because you're getting to the right idea, but it's called the fundamental theorem of algebra. We needed just, I think, 5 zeros. Is that, or is it 3 zeros with a, I don't remember. Hold on, let me see. So which graph could represent a polynomial with 3 real distinct zeros, a different real zero with a multiplicity of 2? What are we going to see if we have a zero with a multiplicity of 2? It's going to, it's got to bounce, right? It's a double root. It's got to bounce there. And so we see a bounce here. We see a bounce here. Right? So each of these graphs has a bounce. Okay? However, what's the issue with this graph? Oh, my bad. Go with the 8s. Sorry. Yeah, there's not 3 different zeros, real distinct zeros, and a different zero with the multiplicity of 2. So this one's out. What's the issue with this one? It's decreasing overall, right? If I connect those ends, that tells me my leading coefficient is negative. That one's out. Could have been the first or the last. So both of those had positive leading coefficients and fit all of the requirements for the zeros. Okay. Ready for number 10? Okay. Number 10, I'm going to go ahead and use number 10 in the place of one of the book questions we're going to look at. So go ahead and make sure you pay attention to this. Again, I've given you solutions. There's a couple different ways to look at number 10. But I want us to talk through some details. First things first. Okay. I've taught you all year that there are how many mathematical representations? Five. What are the 5? Pictorial, algebraic, verbal, graphical, and tabular, right? Guys, if you're not comfortable with the table, what could you make to help you out here? A graph might have been really helpful, wouldn't it? Is that a valid way to approach this? Yes. Is that what I'm looking for? No, okay? But I need y'all to hear me on this because I literally did this in first block, and then I had us do a practice thing, and they looked at me, and they're like, I have no clue how to do this. And I'm like, man, if you just paid attention. Actually, it's not really it. They started on the right path, but they got lost because they ignored my number one advice. Okay, so first things first. You can't always use this. But I have a question. How many roots does m of x, right? So we're focusing on m of x. How many roots does m of x have? How many?
2.
You only think 2? Why are you thinking 2? Is it because of the j of x and the k of x? Okay, so that's something that students in first were thinking as well, but what are j of x and k of x? Those aren't roots, those are, what do we call those things that are being multiplied? They're factors, right? These are my factors that are being multiplied. Not necessarily just zeros or roots. How many roots does m of x have? How many? I can't hear you. You should know. You got 6? Damon, tell me this. What's another word for a root? A 0, right? Guys, look at m of x. How many roots does m of x have? How many zeros does m of x have? Tracy's saying 3. Can you come circle those 3, Tracy? Let's go. Okay? We all in agreement with Tracy that we got 3 zeros right there? What are you confused by? What is that literal output?
0.
It's 0, isn't it? Now, I want to point this out. That doesn't tell me there's 3 zeros. That tells me there's 3 x-intercepts. Hear me again on that. And so Tracy, pay attention to this. There are 3 x-intercepts. -3, 0. -1, 0. 2, 0. Those are all x-intercepts, for sure. Are there any more roots or zeros, though? Where do you see another one, Jeremiah?
There's 2 k of x, another 2 j of x.
So notice, Jeremiah is not just looking at m of x. Jeremiah is pointing out, hey, there's 2 in j of x, and there's 2 in k of x. Okay? I'm going to get into the rate of change in a minute, like I want you to look at it, but I also want you to note, you can make a graph. -3, 0. -2, -4. 1, 2, 3, 4. -1, -6. 0, -6. 1, -4. So 2, 0. What kind of function is that? That's definitely quadratic, isn't it? Cool. -3, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. -3, 10. -2, 4. -1, 0. 0, -2. 1, -2. 2, 0. 3, 4. So, that's a little off, but it'll be fine. So first off, how many zeros do each of the, or how many zeros are there total for the factors? Well, first off, what type of functions are those factors? They're definitely quadratic, right? Lily, how many roots does a quadratic have?
2.
Definitely has 2, right? So if I multiply these two functions together, how many roots are we going to have? We're going to have 4. We need to recognize that each function is quadratic, so each function has 2 roots. So 4 total and m of x is quartic. Right, 4th degree, you can just say 4th degree if you want as well. But why does m of x then only have 3 zeros that we see? Why does m of x only have 3? It has a double root, doesn't it? Isn't this a 0 for both functions? Okay, so it has a double root. We could notice if you make this sketch right here, that you can then, thank you, you can then multiply it like we did last unit. I'm going to mark my x-intercepts to help me visually see what's happening here. All right, what's a positive times a positive? Positive, so to the left here, everything is positive. A positive times a negative is negative, so it goes down into here. Negative times negative is positive. It's got to come back to the 0. And what's a positive times a positive? Because it's a double root, it's going to bounce. What kind of function does that look like? Definitely looks like a quartic to me. So I want us to recognize that we can use graphs to help us figure stuff out, guys. You don't have to just use a table. My whole idea of mathematics is there are multiple ways to approach every problem. Now, make graphs if you need to. Look at the zeros, but be aware, just looking at the zeros here can't tell the whole story. What kind of zeros would I not even be able to see on the table? I wouldn't be able to see imaginary on the table at all, right? So I could make a graph to figure out how many roots there are total, or my recommendation is look at the rate of change. Now, I'm about to show you what almost everyone did that made it really hard and easy to make a mistake. Most people looked here. Minus 16. And the biggest issue people run into is whether they're supposed to add or subtract, how much they're supposed to add or subtract. And if you don't make any mistakes, you can find your type of function right here. Okay? But notice, I haven't gotten to anything constant yet, have I? All that's right so far. Minus 36, minus 12. Have I gotten to anything constant yet? Nope. Okay, so I gotta keep going. See how much of a hassle this is? It's a pain in the butt looking at m of x. And there's a lot of places to make mistakes. Okay, finally got to a constant. If this is constant additive, what is always to the left of constant additive? Not always the rate of change, because my rate of change is all the way over here, but what type of function had a constant additive rate of change? Linear, so what's to the left here in purple? Linear, but we are adding, okay? Hey, what was to the left of linear? What had a linear additive rate of change? That's a quadratic here then, but that's quadratic additive, it's not my function. What function had a quadratic additive rate of change? Cubic. So this is a cubic additive rate of change. Remember, it always increases by 1 power. So what type of function is m of x? It's quartic, or 4th degree, right? 1st, 2nd, 3rd degree, my function is 4th degree. But again, it's easy to make mistakes in there, isn't it?
No.
What if I just looked at the rate of change for the factors, though? That's what I do. These numbers are way easier to deal with. And I saw someone, I don't remember who it was, maybe Jeremiah, actually took these out and moved them over there so that it was easier to see. If I am not giving credit where credit's due, let me know. But notice those are nice and small numbers, aren't they? That's pretty easy to deal with, huh? So then plus 2, plus 2, plus 2. Sweet. If this is constant additive, what is purple? Linear additive.
Linear, right.
Okay? So then what type of function is j of x? Quadratic, right? Okay? Looking here at, what was it, k of x? Minus 6, minus 4, minus 2, plus 0, plus 2, plus 4, plus 2, plus 2, plus 2, plus 2, plus 2. Constant additive, linear additive, so k of x is quadratic. And once again, if I take a quadratic and multiply it by a quadratic, I have how many zeros? 4 zeros,
4.
and so fourth degree. So, here's the thing. Is there only one way to do this? No. But, once again, if you are looking at the rate of change for m of x, there are lots and lots and lots of places to make mistakes. If you look at the rate of change for your factors, it's going to be easier, personally. Alright? Now, we need to get some practice actually applying this idea. So quickly before lunch, I want y'all to look at this question from the textbook. This is number 4 on page 259. I want you to go ahead and work with each other. I want you to figure out what type of function v of x is, right? So 259, number 4. I'm going to leave this up here for now in case anyone wants to take a quick note. Amy, you might want to get up, move around, get that blood flowing so you don't fall asleep on us. Yes, ma'am. You can't wait 5 more minutes? This and review. Recording? No. So like right here we have the right idea that we have a quadratic, and so we have a quartic, but be careful. The reason why we say an additive rate of change is because we are literally what? Adding, right? But when you get to the function itself, are we adding? No. So this is not a quadratic additive. Notice this is the same, so it is constant additive, then linear additive, then this is a, breaking my calculator, quadratic what? Function. Notice guys, we're not adding or subtracting here at all. It's not a rate of change there, that's a function. Okay? So remember when you get to the end and you get to t of x, that's function notation, that's a function. Same thing again here, quadratic function. And so all around the room, for those who have gotten there, when we take a quadratic and we multiply it by a quadratic, what do we end up with? A quartic. For a couple of reasons. A quadratic always has how many roots? 2. And we multiply it by another quadratic with 2 more roots for a total of 4 roots. You can also see it as x squared times x squared gives us x to the 4th. So lots of ways to see it. Pay attention to rate of change. So can we also, I just got to ask, is it easier just looking at the factors than it is looking at the final function? Yeah, there's a lot less going on there, okay? Couple of things I want to point out really quickly. First off, did we see any zeros in this table? Did you see any zeros in the table? No, I don't see any. What does that tell us about our 4 zeros? They're imaginary. Notice, what did I create right here? I created a graph. I graphed t of x, now I graphed w of x. What kind of zeros or roots does t of x have? They're imaginary, they're not intersecting the x-axis. What kind of zeros or roots does w of x have? Imaginary, they're not crossing, it's not intersecting the x-axis. And so that's why we don't see any zeros right here. But once again, a quadratic times a quadratic gives me a quartic, right? Second degree and second degree gives me a 4th degree. One thing I do want to point out, because I don't think we've talked about this in a while, does anyone know how they're getting this negative 44 in the table? Or this negative 18 or this negative 12? Yeah, what are they multiplying? Okay, let's look at that. We want to notice they're taking t of x, they're multiplying it by w of x. What's 4 times negative 11? Negative 44, right? What's 3 times negative 6? What's 4 times negative 3? Negative 12. Again, we need to recognize that literally what we're doing is we're taking one function and multiplying it by another function. That's it. Okay? Questions, comments, concerns? Okay. So, look at your factors, look at the graph. Like ideally I want you to look at the rate of change, but if you create a graph out of it or something like that, that can work as well. Okay, so we're going to move to page 263 for our final little thing with this unit before I start showing you some stuff with the next unit. And so here's what I want us to do. Yeah, I'm not going to do that because of time. So let's do this graph. Does that graph look familiar?
Yes.
Where have we seen that before? On the DYU, that's where I got this graph from, actually. So, we've already used the zeros to write the polynomial in factored form. I think it was 1 for the A times x plus 2 times x plus 1 times x minus 2 times x minus 3. And the standard form was, thank you. What came after the x to the 4th? Minus. That's yours. Okay. Minus 2x cubed minus 7x squared plus 8x plus 12. Okay. So we got our standard form there. Now, what I want you to do, one, you can get out the sheet of paper that this is from. Page 263, or if I need to print it, I can for a handful of us. I want you to do two things, or not two things. I want you to do degree in behavior. Not as worried about that. It'll take no time. Do this, domain and range, and I want you to also identify the relative extrema. I would say relative and absolute extrema. And finally, domain intervals of increase, decrease. That'll be what wraps us up for this unit. So, let's say 14 minutes max. I would like to be done in 10 minutes though. Okay, so we got several things there to work on. Let's go ahead and get up to our vertical surfaces, identify those different things. Again, does anybody need me to print out a copy of this? Because we never tore it out of the book. Or in that interval notation in general. The minimum, then the maximum. Range, minimum y is -4, maximum y is infinity. Pay attention to those details. Okay. You guys make sure you close the doors. There's AP exams going on down the hall. Alright, so that's our domain and range. Now, I want to just point this out. This group up here did a really good job of marking their extrema. Now, I need to point this out though. Is this right here a max? It's okay to make mistakes, we just got to learn from them. Is this a max? No, what's happening right here? I'm going to color code it. It's what? Say it louder. Increasing, there we go. Okay. So all the way through, it's increasing. Meaning, remember that slope of the tangent line is positive. So increase, is there anywhere else this graph is increasing? Which side? The far right, okay. So what's happening in these unidentified regions? It's decreasing, okay? And this is important to pay attention to because, one, I'm going to ask about those intervals of increase, decrease later, but two, if this is decreasing, this is increasing, what does that make this? A relative minimum, right? The fact that this is decreasing and then starts to increase makes this a relative minimum. So remember, I was talking about this with one group. When I say extrema, yes, extrema are at turns. But what are the two types of extrema? Maximum and minimum. You got to identify those, okay? And remember, it's all rooted in it stops decreasing and starts to increase. The fact that it stops increasing and starts to decrease makes this a relative what? Maximum. Now, is that the absolute maximum for this graph?
No.
Why not? Why is there not one? It keeps going up for forever. Can you get more than infinity? No, so that's not an absolute maximum. Do we have an absolute minimum though? Where? Or what value? That -4 in here, right? Also absolute. Now, I'm going to pause, I'm going to point this out. Those are estimates based off our physical graphs that we see here. What would I need to look at to get a more precise, I would have to look at a calculator, so don't forget. We look at a calculator to get more precise. There will be a portion of your test that is non-calculator. There will be a portion that is calculator, so you can use a calculator like this. So let's see if our estimates were actually right. I think they're close, but I'm not sure if they're 100% right. So remember, you can find zeros here, you can find a minimum. So notice lower bound, I gotta go to the left, enter, go to the right, and enter. So our y value was correct. Notice the x value is just off by a hair. Pretty darn close though, right? But notice if we want to be more precise, we have to use a calculator. And even that, very, very close to 14, but just a little bit off. So, Mimi, what do we got to use to be super precise? Got to use a calculator, right? But the justification off the graph will be more than enough evidence, but precision requires a calculator. Until you take a calculus class, and then you actually learn how to find that algebraically. Dot is like, no, I'm good, Mr. Kenny. Yeah. It's cool. I enjoy it. It's a fun class. All right. Last things though. So we've got our absolute and relative extrema. What other feature are extrema really helpful in helping us find? Domain intervals of increase and decrease. Notice we already did decrease, we labeled it, right? And so it starts decreasing way over here. So where does it start decreasing? Negative infinity. But it's going up, so why is it negative infinity? Say again? It's to the left. I need you to remember, what kind of intervals are they? What kind of intervals? Domain intervals. Madison, when we say domain, are we talking about x or are we talking about y? Say it louder like you believe it. It's x, there we go, right? Domain intervals are x values. Yes, the y values are decreasing, but I'm asking you, what's the x where those y are decreasing? So, it starts decreasing from way over here, and where does it stop decreasing? Remember, that's the whole point of that relative minimum. It stops decreasing and starts to increase. Now, again, you can be more precise from the calculator, but there we go. After that, Mimi, after it stops decreasing, what does it start to do? Starts to increase. And it starts increasing at -1.5. Right? Exactly where it stopped decreasing is where it starts to increase. And so where does it stop increasing? That's the whole point of a relative maximum, isn't it? That's where it stops increasing, at the relative maximum. Okay? And then after that it starts to decrease from that 0.5 to 2.5. And then from 2.5 on, it is increasing the whole way. That's our unit. Identifying those features. Most of that will be on a calculator portion of the test, unless I identify all the features for you and like put points on the graph. But it will probably be on the calculator portion of the test. Questions? Shada, you look like you get a question.
So for the end behavior, putting left side be negative infinity? Because you were talking about earlier, but they have positive, so are we wrong?
So look at it right, or look at it again. This is as x goes to infinity, y goes to infinity. That would be my right hand side. Over here it's as x goes to...
Oh, I was looking at their work.
Right.
You were basing on
And so I will say that, like, it is better, guys, if you label it, but I was able to look here and know, oh, that's the left-hand side. because I understand how to read, even though this is on the left side of what they wrote.
That's not what I was looking at.
What were you looking at?
I was looking at their work. I thought you were talking about their work.
Where?
On the right side on top, because you were pointing at it.
Oh, this?
So yeah, I thought you were talking about their work.
Gotcha, no. All right, questions? All right. So that's it there. You can go ahead and clear all that stuff off your desk. I'm about to pass out what we're gonna work on for the last 10 minutes or so. Now, this is honestly just something that we're gonna be able to touch on. Not gonna be able to honestly really assess, but the lessons I chose are not lessons I've ever done before because they are designed to help us review some of what we have studied earlier this year. And so, please take advantage of what I have selected to help you review. Alright? So I'll explain what that means. I'm going to skip through this so we can get to the lesson. So here we got Funky Fro-Yo. The school jazz band is playing at Sweet Yo's, a frozen yogurt shop. It costs $5 to get in the door for the event. If you'd like to eat Fro-Yo to eat while listening to their tunes, you can fill your cup with yogurt and toppings for 40 cents per ounce. Write an equation that gives the total cost in dollars of attending the event if you order Z ounces of Fro-Yo. So do notice D equals, and do we know how many ounces it is? It's an unknown, it's variable. What I want you to do is I want you to work within your small group for just a minute, maybe 90 seconds. Try to come up with an equation for what D is equal to. Come around, see what y'all are working on, what you're thinking. So let's come up with an equation together. By the way, guys, I know you're still sitting, and that's fine, but still talk with each other, help each other.
So, honestly,
So one thing to remember is we are using Z to represent ounces. Make sure you're prepared to discuss and explain where that comes from. Do you know where that came from, Damon? Where did that equation come from?
where's it off the bat?
40 cents.
Per ounce. So it's 5 grams.
So why is 40 cents per ounce and it's 0.4 Z?
Off the bag business.
Off the back business.
Keep thinking on it.
Because it's not
So you gotta pay $5 when you.
So what are we thinking?
And then.
Okay.
Okay,
So why is it 5x? Okay.
The X would be.
So where's the
how many
5x
ounces
come
you
from?
Each, okay. It's gonna be plus 5.
So 5 times 0.4.
$5 when you first
Okay.
get paid.
Okay. All right. So, I just want to point something out. So, there's a few different ways that you can tackle this and approach this, but I want to look at what I see Caleb writing up here because I think this would be a good starting point. Caleb wrote y equals mx plus b, and did you also write a times b to the x? Is that right? Well, what is Caleb referring to when he writes y equals mx plus b and y equals a times b to the x?
Linear.
Linear, which one's linear? Y equals mx plus b, and a times b raised to the x is exponential. I'm really glad you brought both these up. So, is this relationship linear or exponential? Exponential, I heard. You think linear? Okay, we made claims. Where's our evidence? Okay, 5 is by itself. Okay. I don't disagree necessarily in any way, shape, or form, but for the sake of time, let me ask you this. What's another way I could represent this situation to make sense out of it? Could I make a graph? Okay, I can make a graph. Graphs are not always the easiest thing to make to start from, but can we make a table? Okay, so if I'm talking about a table, okay, I got my Z ounces, I got my D dollars. Even if I don't pay a single or buy a single ounce, how much money am I spending? Spending $5, right? If I get 1 ounce of froyo and toppings, how much am I spending?
$5.40.
I would say I'm spending another 40 cents or $5.40. If I buy a second ounce, how much is just that second ounce going to cost me? Just the second ounce. Not first and second ounce, just the second ounce. Is it another 40 cents? Which gives me that total of 80 cents, right? So if I go to 3 ounces, I'm at $6.20. 4 ounces, I'm at $6.60. Notice we can plainly tell when we do this, what rate of change do we have? Not just additive, constant additive, making it what type of function? So we're going with a linear idea. So remember, tables are great for rates of change. I can make a graph as well. If I can see that graph happening, it would give me a line. So I still need what 2 things from that equation though? I need the M. Well, and the X, I don't really need, I already have-ish, which we're not going to use X, by the way. What are we going to use? Z, okay. What do I need then? I need the M and the, someone said B, yep. What is M though? That's the, M is always slope. Which it is, how much? 40 cents. Now, I will point out, in this case, I would always use the change in Y divided by change in X. How many ounces are we changing by each time? 1. I do bring this up because let's say I didn't do every ounce. Let's say I jumped from 0 ounces to 4 ounces, then that'd be an extra $1.60. Split over 4 ounces though, you know what I get? 0.4. Notice that rate of change doesn't change once you simplify it, right? So it's still 0.4 Z. Plus, what is B? Say it louder like you know it.
So Y-intercept, which is 5.
There's my equation. The amount of money you're spending is 0.4 times however many ounces of froyo you buy, plus that cover to get in of $5. Okay. So from here, we got 2 minutes. If your cup weighs 14 ounces, how much would you pay in total? How would you figure out that answer?
By plugging in 14 for Z.
Notice that's ounces, right? That's saying Z is equal to 14. What's another way to say plugging in? Substituting it in, yep. You're good. Notice I use my function notation to say D of 14 is equal to 0.4 times 14 plus 5. If I remember correctly from earlier today, it comes out to $10.60. But here's the question for you that I need to end on. Shayla brings $10 for the evening. How could I figure out how many ounces she could buy if she has $10? Okay, I could substitute 10 in for the what? For the what? Isn't that her dollars? Can I solve that equation to get how many ounces she could buy? Yeah? Hey guys, we still have a minute. Chill for a second. Number 4, Samra only has $7 to spend. How can we figure out how many ounces she could buy? Substitute 7 in for the dollars. Tonight, I need you to, because this is where we're going to pick up tomorrow, find out how many ounces each of them can buy. Find out how many ounces each of them can buy. How can we do that? What would be the strategy we want to use? Something you've been doing since middle school. It's something we've done this year. I can use inverses, can I? Inverses with what? Properties of equality. So notice this is linear. That's why I tackled this problem, because I need us practicing linear. You got to be on the lookout for that constant additive rate of change.